All right, let's continue on with number 12 through 15. This one you're asked to write the polynomial given in standard form, then identify the degree, the leading coefficient of the polynomial, and classify the polynomial by the degree and number of terms. So this one's related to that vocabulary that we went over. You can refer to section 2.1 if you're still stuck with any of that. Standard form again means that the term with the highest exponent gets to go first. So if we look at this first polynomial here, notice this one has a variable, even though we don't write that exponent right, it has an exponent of 1. So the x value actually gets to go first, so negative x, and then the positive 6 will go second. Looking at that, our degree there again is the highest exponent of the polynomial's terms, which is 1. And our leading coefficient is the number that is leading the polynomial. So even though we don't write a negative 1, that essentially negative represents a negative 1 there. Again, it's the coefficient, so not the variable part. And then this one is a degree of 1, which means it's linear. And then there's only 2 terms, so we're going to call it binomial. So this would be a linear binomial. Okay, number 13. Again, the highest exponent within these 3 terms is the 3, so this term right here gets to go first. We're going to write 5p cubed. The p squared is the next largest, so negative 3p squared, and then the constant, or the number without a variable, goes last. That means that our degree, again, is that highest exponent, which is the 3, and the leading coefficient is the number leading once it's in standard form, so that would be a 5. And this one is a degree of 3, which makes it cubic, and there's 3 terms, so we would refer to it as a trinomial. Okay, 14 again just has these 2 terms, and the highest exponent is 5, so we're going to do the 13x to the 5th first, and then negative 6x squared gets to be the second term. That means that our degree is 5 in this case, and the leading coefficient, or the number leading the polynomial as in when it's in standard form, is 13. Degree of 5, remember we called that a quintic, and there's 2 terms, so again this one would be a binomial. The last one, just 1 value, so we're going to call this standard form there. He's his own term. The degree on this one, if there's no variables, is 0. He's his own leading coefficient, and this one is just a monomial, but because there's no variables and the degree is 0, we call it a constant monomial. Okay, make sure we're comfortable with all of that terminology and that we're very comfortable with putting it in standard form if asked to do so. Notice the next section asks you to perform the indicated operation and write the final expression in standard form, which will be asked of you on your test as well. So we talked about when we look at polynomial operations, we need to look right between them and see what operation it's asking us to do. If the parentheses are next to each other, that's multiplication. If there's an addition sign here, we're just combining like terms. If there's a subtraction sign, we need to take care of the negative and then start to combine like terms. So just recognizing which operation is being indicated. On this first one, we're looking at multiplication. So again, remember that I'm going to rewrite this. When we multiply, we distribute every part of the first term to every part of the second. Every term in the first polynomial to every term in the second. So we start here with this guy, and he's got to multiply by both terms in the second polynomial. X times x would be x squared. X times negative 4 is negative 4x. We then do the same thing for the second piece, so it has to multiply by each piece in the second polynomial. So 6 times x would be 6x. 6 times negative 4 is negative 24. Our last step is to combine like terms if we can. Those 2 middle terms both have x values, so we're going to leave the x squared in the front. Negative 4x plus 6x would leave me with a positive 2x, and then we're subtracting 24. Again, 17, very similar, so we're multiplying here, and we get 4y squared. Y times 8, we get 8y. Negative 5 times 4y is negative 20y, and negative 5 times 8 is negative 40. Again, we have 2 terms in the middle that will combine, so we've got 4y squared minus 12y, subtracting 40 there on the end. Number 18, again, we look in the middle here, and this is implying addition. Addition just means we combine like terms. So we have 3a in the first polynomial and a in the second one, so 3a plus another a would give us 4a. And we've got 7 and a negative 1, which when we combine those through addition, we get 6. 19, also addition, so x squared plus 2x squared would be 3x squared. We've got a 6x that doesn't combine with anything, so we just bring him down. And then negative 5 and a positive 15 would leave us with a positive 10. Number 20 is subtraction, so we want to make sure that we take care of that negative first, right? It's going to affect that second polynomial, so that's like a negative m squared, a positive 5m, and a positive 2, and then we're going to combine like terms. So we've got a negative m squared and a negative m squared, which would give me negative 2m squared. Positive m plus 5m is 6m, and then the 2 plus 2 would give me a 4 there at the end. Again, 21, same idea, so you've got a negative 6p squared and a negative 13p. So when you combine, that 6p squared doesn't have anyone to combine with, so he gets to lead the pack since he has the highest exponent, and we want to write our final answer in standard form. The p and the negative 13p, that would be negative 12p, and then our positive 7 there at the end. Again, these last two, notice they are multiplication, so you can build a box or you can FOIL distributing. So we go x times x squared, remember that gives us x cubed. X times 7x would be 7x squared. 4 times x squared would be 4x squared. And 4 times 7x would be 28x. Again, you've got some like terms there in the middle, so we're going to have x cubed plus 11x squared plus 28x. Number 23, again, this is multiplication. We did talk about using the box method if you want to use the box method. Okay, that's a terrible box. We can organize it, right, in a box, and our first polynomial could go off here to the left. Each term gets its own row. And then there's 3 terms in the second polynomial, so they each get their own column. And then we multiply to fill in that box. So negative 3y times 4y squared would be negative 12y squared. Negative 3y times negative y would be a positive 3y squared. Negative 3y times negative 7 would be a positive 21y. Moving down to the second row, 1 times 4y squared is 4y squared. 1 times negative y is negative y, and 1 times negative 7 is negative 7. We like this because it organized our terms for us, right? Those are like terms on the diagonals. So when we pull it out, we'll start with the negative 12y cubed, because it doesn't combine with anything else. Oh, I said cubed, and then let's make sure that's cubed there. And then 4y squared plus 3y squared would give me 7y squareds there. And the next column or diagonal would be negative y plus 21y, which just leaves me with 20y minus 7. Now again, you can just distribute on that one if you'd like to. Again, just take the 3y and multiply it by each piece. Do the same thing with the 1, and you'll end up with the same result. Okay, down at the bottom, writing a piecewise function for the graph. Be sure to use appropriate and accurate function notation. So again, when we write a piecewise function, we start by naming it. You can call it f of x, p of x, h of x. You can even use something other than x as long as we're consistent, and then it equals, and then we draw those braces. Notice our graph on the left has 2 pieces. So even though it has a dot right there, right, that doesn't change the slope at all of that piece. So we're going to call that all one piece. And then you've got a piece here. Notice that the barrier or our domain restriction is there at positive 4. So I'm going to just write that 4 so that I remember. So we know that this piece on the left, right, this arrow points left, is less than 4. And the piece on the right is going to be greater than, and it's a filled in circle, so we're going to be greater than or equal to 4. So we've got our 2 pieces, one again on the left side of 4, one on the right side of 4. Now the one on the right side of 4 is just a flat line at positive 1. So his equation is just a positive 1. He's always 1, no matter what. The other one, we do need to find the slope. So notice this one goes up 1 before it runs 4. Oh, that's a terrible drawing there, my bad. It's going to run 4. So if we go up 1 over 4, we've got a slope of 1/4 x, and then our y-intercept is crossing at 2, so we would say plus 2. Again, when you're writing these, right, these are linear pieces, so they fall in the form mx plus b, where this is the y-intercept, where is it crossing the y, and the m stands for the slope. So you need those two pieces, and then you can build your function. Moving to the back, we've got some linear ones and then more piecewise. So on this, again, just reviewing that same linear piece that we just used, it says, given the following graphs, find the slope, y-intercept, and then write the equation in that slope-intercept form. So that's slope-intercept form, y equals mx plus b. On this first one, again, we find 2 lattice points when we're counting the slope, and we move from the left point that we found crossing to the right one. So notice this is going to go down 2. And then it's going to go to the right 3. So our slope in this case would be a -2/3. The y-intercept, again, if you look at the y-axis, it looks like the function's crossing at -5. So our y-intercept would be -5, or as a point, we could write it as 0, -5. Okay. And then lastly, we would write our equation. So we put in our slope multiplied by x, and then plus b. Our b is negative, so I'm going to put subtract 5. That would be our equation. There's our intercept, and there's our slope. Same idea on the next one. Again, find 2 lattice points that work. Moving left to right, we would go up 2, and then we would go to the right 3. So this time it's a positive 2/3 slope. And again, finding that y-intercept, it looks like it crosses at 3. Or if we wrote it as a point, that would be the point 0, 3. And our equation then would look like 2/3 x plus 3. Okay. On to piecewise functions again. So this time we're graphing and evaluating them. So first of all, let's talk about graphing. We talked about in class that maybe it's helpful to draw a little line at the barrier if it helps you. And in this case, notice the domain restriction. 1 is on the left side or less than 0. The other piece is going to be greater than or equal to 0. So this is actually our restriction right here. So I'm not going to draw it in on this one, but essentially that's the barrier. One of them is going to exist over here and one of them over here. Remember, they can't both head in the same direction or on the same side of that barrier. If they do that, they are not a function, so we want to make sure. So we can use just the y-intercept and the slope to graph if we want, because this one's touching 0, so that's going to be helpful. So let's start at our y-intercept here. The y-intercept is at 2, and it looks like it's going to be an open circle on the y at 0, and then it looks like we have a slope of 6. So if we count 6, notice if I were to go up 6, 1, 2, 3, 4, 5, 6 over 1, that's going to break into the right side of this barrier. So we want to go down 6 and over 1. Going that opposite direction still allows us to create the same function, just the other piece of the function. So we're headed this direction. Okay. And then on the right, again, our y-intercept for this right piece is at positive 3 with a closed circle. And it looks like our slope is -2. So again, instead of going up to left 1 and breaking the barrier left, I'm going to go down 2 and then right 1, down 2, right 1. And we can just check to make sure that our slopes are correct as we're going through that. And then 27 part B, if I want to evaluate the function, again, we did this on the first page, but just remember that 4 only fits into the domain of one of these functions. So if we look up here at our restricted domains, we check this and say, is 4 less than 0? It's not. Is 4 greater than or equal to 0? Yes, so we're going to use this piece right here to evaluate the function. -2, we put in 4 for x, and plus 3. That would be -8 plus 3. In this case, it looks like we're going to result in -5. Okay. Then we look at g of 0. If we look at our domain restrictions, notice 0 is not less than 0. but 0 is greater than or equal to, so we're actually going to use the same piece. We have -2 times 0 plus 3, which -2 times 0 is just 0, so that's going to be a positive 3. Number 28, graphing. Notice these domain restrictions, and I'm going to draw these little barriers in just to kind of help us. But notice one of them is always x is less than -1. So there's going to be kind of a barrier or a split between our pieces at -1. The next one goes from -1 up to 2. So then we're going to have another kind of restriction here at 2. And the piece is going to exist between those. And then the other one is on the right side, or when it's greater than 2. Because this one doesn't cross at 0, I'm just going to plug in my domain values as we practiced to kind of help me with that part. So let's look at that. Again, if I want to know where to start on my barrier, I just take this domain value and I put it into the function. So -2 times a -1, when we plug that in, is just a +2. So on my barrier, the left one, I'm going to start at +2. Now it doesn't include -1 in that domain restriction, so it's an open circle. And then let's use our slope of -2. So we're going to create a slope of -2. Again, notice that piece stays solely on the left side of that barrier. Then we go to the middle section. So again, if I want to figure out where to start and where to end, I can start by plugging this into my function. So 3 times -1 minus 1 would be -3 minus 1. This looks like it's going to start at -4. So I'm going to go down to -4, and we're going to put a closed circle, it looks like, at -4. Then we can do the same thing with the other side. Put 2 in here for x. 3 times 2 minus 1 is 6 minus 1. So it looks like we're going to be up at 5. And again, that looks like it's a closed circle. Now if I start to draw this graph, notice that it is going to have a y-intercept of -1, just as we see in the equation. So that tells me that we are in the right spot. So we're going to go here, up through -1, and up there. And again, if you want to check that slope, you know that you should have a slope of 3. So notice it's going up 3 over 1, up 3 over 1. That piece looks good. Then on the right, again, let's plug this domain value in. So we're going to take this 2 and plug it in. If we do -1/2 times 2, that's just equal to -1. So at -1, I'm going to create an open circle on this barrier. And then again, that has a slope of -1/2. So I'm going to go down 1 over 2, down 1 over 2. And we create this piece here. Again, when I get done, I just make sure that nothing broke through any of the barriers. I'm going to erase the barriers. They really aren't a part of our graph. We just draw them to kind of help us. Oh no, I erased part of the function. Just to help us draw the piece. So we just check that it passes the vertical line test. Remember, the vertical line test says it can only hit the function once. So notice it's hitting that guy, and then when we get to this part, it's hitting this one, but it's never hitting 2 of them at once. All right, lastly, evaluating these last two, we're doing f of 3. So if we look up here, it looks like +3 is going to be greater than 2. So we're going to use this piece on the bottom. So we're going to have -1/2 times 3, which is just going to give us -3/2. And then f of -1. It looks like -1 is going to be included in this middle section, so we're going to use that middle function. 3 times -1 minus 1. So -3 minus 1, we know, is at -4. And notice that matches our graph, right? So when the graph is at -1, our function is filled in down here at -4. Okay, I hope this was helpful. I'm sorry I'm kind of losing my voice.